How can an element's position on the periodic table determine its properties? It's a very deep question, so let's see if we can answer it with the next few slides. We're going to start with a few uh, definitions of the periodic table. The first one being group and periods. When we talk about groups on the periodic table, what we're really doing is we're talking about columns. There are 18 columns on the periodic table, and as scientists, we call them groups. Period, on the other hand, period represent rows on the periodic table. Rows, there are 7 of them, but we call them periods, which is, again, part of the name periodic table. So rows are periods, columns are groups. A couple more definitions. There are main group elements and transition elements. The main group elements, if you look at the periodic table, sit higher up. So they're the ones here in red on my screen. The main group elements, the reason we call them this is because they follow a lot of set of rules. They're pretty predictable. When we talk about the main group elements, they're mainly what we're talking about in this kind of chemistry class at high school. Now, we'll also talk about the transition elements a little bit, but they sit lower on the periodic table, and sometimes they break the rules in terms of following trends and things like that. We'll learn about that later when we talk about like charges, how they don't follow a set charge. They're less reactive. They're kind of sitting towards the middle of the periodic table. All right, the first idea, the first trend we want to look at is element families. Now here on my periodic table, this is a more colored version of the periodic table. Hopefully your periodic table is colored as well. By the way, if you have your periodic table, you should consider pulling it out. If you don't have a periodic table, there is some found in the course resources on Schoology. You should consider maybe opening that up and printing it if you have the availability to do that. But there is one there if you need it. Now, families are groups of elements with similar properties, specifically similar chemical properties, and they're found as groups on the periodic table. So these are different families. Now, some of the families, like in group 13 through 16, don't follow a strict column guideline, but they're pretty close. And all of these elements have, like I said, similar chemical properties, like the alkali metals explode in water and the halogens are all gases. So the reason this happens is because of valence electrons, which we'll talk about in a minute. But let's talk about reactivity. Families are very reactive together. And in fact, the most reactive metal family is this group right here. It's called the alkali metals, and it's found on the edge of the periodic table. The other most reactive family is called the halogen, and it's found pretty close to the right edge of the periodic table. So families in groups 1, the alkali metals, and group 17, the halogens, are the most reactive. Now, the noble gases, the ones on the very end, group 18, they are not reactive. They're the least reactive group on the periodic table. As we go in towards the transition metals, they get less and less reactive. So the transition metals are reactive, they're just not very reactive. Now, all of this is due to an element's valence electrons. So let's look at those right now. Now, valence electrons are electrons that are found in the highest energy level of a Bohr model. So if you look down here, this is carbon's Bohr model, and you can find carbon in group 14. Now notice that carbon, silicon, germanium, tin, and lead, all of them have 4 valence electrons. So families or groups on the periodic table all follow similar valence electrons trends. That's because every time you draw a new ring on a Bohr model, we start over with the electrons. So these electrons, by the way, are responsible for an element's chemical properties. So this really explains why halogens, we'll learn later that valence electrons can be taken away or given, but the reason for this is alkali metals with their 1 valence electron, they want to get rid of those electrons as quickly as possible, and so that's why they're super reactive. On the other end, the halogens are super reactive also because they have 7 valence electrons, and they're going to steal 1 more. So again, we'll learn later in this slide about electronegativity, talking about an atom's want for electrons. These electrons specifically are also involved in bonding with other elements. So when lithium wants to bond with chlorine, this is what the electrons that do that, these valence electrons. We'll talk about bonding in a later unit. Next is orbital groups. These represent the subshells in which the element's outermost electrons reside. So if you remember, orbitals or suborbitals are just the physical 3-dimensional shapes that electrons take up. When we say electron clouds, those clouds take up specific shapes. And you can see those shapes down here at the bottom with the S shape, the P shapes, the D shapes, and the F shapes. They get pretty crazy. I'm not going to focus too much about electron configurations and writing the electron configuration subscript right now. I just want to show you on the periodic table that we're organized in that aspect as well. And so these two columns, columns 1 and 2, or groups 1 and 2, their highest energy electrons are in an S shape. Columns in group 13 through 18 are in the P shape, and then the transition metals are in the D shape, and the lanthanide and actinide series, which we kind of consider transition metals, make an F shape. All right, how about metals, nonmetals, and metalloids? On the periodic table, most of the metals are found on the left-hand side. It's these red ones right here. These metals are shiny, or they're lustrous. They conduct electricity or heat. They're malleable, meaning if you hit them with a hammer, they bend instead of shatter, and they react with acid. The nonmetals are these yellow ones right here. These nonmetals are these metalloids, I apologize. These metalloids right here are the yellow ones. They're kind of have properties of both metals and nonmetals. The blue ones are nonmetals. They're dull, non-conductive, they're brittle, and they don't react with acid. Now, how can you tell where they are in a periodic table? Well, you just got to follow this line right here. There's this stair step right here. Everything to the left of the stair step is a metal, that's all the red ones. Things to the right of the stair step are non-metal, and most things touching the stair step are metalloids. Now beware of some exceptions. For example, hydrogen is over here because of its one valence electron. It's with this family right here, but it's a non-metal. Hydrogen is a gas. Aluminum is another weird one. It's touching the stair step, but it's definitely a metal. It's not a metalloid. On your periodic table, in the lower left-hand corner of the front, you can see there's a family groups. You should consider maybe writing which family groups are part of which metal, non-metal, or metalloid group on the periodic table. All right, next is atomic radius. I'm talking relative atomic radius. Relative means compared to each other. We're not going to go into the specifics of what specifically the atomic radius for each of these, like what the picometers are and the specific numbers. The radius, by the way, is just the halfway point between the center and the side, so it's the measurement basically of the size of an atom, if you were to think of an atom as a sphere. And so the elements on the lower left-hand corner of the periodic table are larger, and the ones in the upper right-hand corner are smaller. So the trend increases towards the bottom left. So in a test, if I were to give you a set of elements and say, hey, put these in order from smallest to largest, this is how we would do that. We would use the periodic table and the relative position from each other to be able to figure that out. All right, electronegativity. Electronegativity is an atom's ability to attract electrons. And so we talked about those valence electrons and how elements either want to get more or want to get rid of them. So elements with 4 to 7 valence electrons have a high electronegativity. So that's these guys up here, mostly the nonmetals. These guys up here have a high electronegativity. They really want more electrons, and so they'll do anything they can to get it. In the lower left-hand corner, on the other hand, or the left side of the periodic table, we have low electronegativity. These guys typically want to get rid of their electrons. They're not really attracted to them. This explains reactivity. This explains bonding. It's a really important concept with a lot of the previous trends we talked about. Now notice that the noble gases they don't have, their electronegativity is null because they don't really attract electrons and they won't get rid of electrons. They are non-reactive. They're set in stone and they have all the electrons they want with 8 electrons.